Alright everybody, welcome back. In this video we're going to talk about areas involving polar curves. And we start first by identifying the formula that we're going to use to find the area inside of a polar curve. The area is going to be the integral from alpha to beta of 1/2 the radius squared times d theta. And actually, if you think about it a little bit, where we get this formula from is reasonably simple. What we're doing is we're dividing this region up into a little circular wedge like so. And the angle in here is the change in theta. And then if we want to look at how we find the area of a sector like that, what we're really doing is we're taking the area of the circle times the portion of the circle that we're looking at. And since the angle of this little wedge is d theta, the portion of the circle we're looking at is d theta over the entire angle formed by a circle, which in radians is 2 pi. And then multiplying these two things together, we end up with 1/2 r squared d theta for the area of that little sector, and then we use the integral to add up all of those infinitely narrow circular sectors. Alright, let's look at example 1. We're going to determine the area of the inner loop of this polar curve. So I'm going to take a look at what this curve looks like. I'm going to get myself into polar mode here. And so I'm graphing 2 plus 4 cosine of theta. And as far as my window goes, yeah, that should be plenty to get a look at this. Alright, now let's zoom in a little bit, because I don't need that big outer loop. I'm trying to determine the area of this inner loop. And so what I'm really looking at here is the area inside of this loop right here. Okay? So we know the equation that we're going to use for this loop is the equation that we have from the function. So I'm going to have 1/2 times the integral of r squared d theta. And now all I need is the angle measures for this. And in order to find that, I'm going to trace my way around the curve and see where this loop starts. I'm going to zoom back out. If I could hit the right key. Zoom back out. Now I'm just going to trace this curve and find where this inner loop starts, angle-wise. And you can probably figure it out if you think a little bit. But it starts right there at the origin, which is a theta value of 2.094. If you don't recognize that number, that's 2 pi over 3. So that's going to be our lower limit of integration. It's 2 pi over 3. And our upper limit of integration to find the area inside this inner loop, I'm going to go around till where we get back to the pole, and that's at 4.189, which is 4 pi over 3. Okay, and if you have trouble going to those approximations, one thing that you can do is just take that value that you get, 4.1887902, 4.188. What was it again? Oh, darn it. 7912, I think it was. Hope I'm picking the right value. If we take this value that we get from our calculator and divide it by pi, you see we get 1.3 repeating, and we get some extra digits because of rounding there, but we get 1.3 repeating, which you should recognize is 4/3. That's kind of the way that I would find those as exact values if I was looking for them. Okay, now we have our integral set up. So in order to find the area inside this inner loop, I'm just going to go ahead and integrate this. So the integral of the quantity 2 plus 4 cosine of theta, quantity squared, with respect to theta, from 2 pi over 3 to 4 pi over 3. And we get 4.348 for the area inside of that inner loop. Alright, there's your first example. Let's go on to example 2. When we have regions that are inside of a curve but outside of another curve, we're going to use a very similar concept. Sorry about that. We're going to use a very similar concept where we use the outer radius squared of the region, the outer boundary, and take away the inner radius. In essence, what we're doing is we're taking a circular sector and subtracting away a smaller circular sector inside of it that forms the area between those two curves. All right? Oops, wrong key. All right, example 2, we're going to determine the area that lies inside r equals 3 plus 2 sine of theta and outside r equals 2. So we're going to look at a graph of this. 3 plus 2 sine of theta. Sorry, my voice is going in and out on me today. Alright, and I look at the graph of these two curves. There's the first one, 3 plus 2 sine of theta. And there's the second one, r equals 2. So what we want is we want the area inside of the bigger circle and outside of the smaller circle. So if we take a look here, the area that we're looking at is this area in here. Okay? And on that interval, the first function is going to be our outer curve and the second function our inner curve. And so when we set up our integral, it's going to be the integral of the outer curve squared minus the inner curve squared. And then I just need, did I forget my 1/2 in the first example? I did, didn't I? Oh no, I didn't. Did I forget it on my calculator? I don't remember. I think I might have. If I did, I may have forgotten to multiply by 1/2 on my calculator. Adjust accordingly. I'm not going to forget this time, I hope. Alright, so if I look back at the graph of these, now I need to figure out, by tracing the curves, where the intersection point of these is. And I can't go backwards, so I'm going to find the upper limit first, which occurs over here where these two curves intersect, which is right there at 3.665194. If you don't recognize that, 3.665194. 3.665194. It's 1.6 repeating. which is 7/6 pi. 7 pi over 6. And the other limit of integration, if I go back to my graph and trace around it, I forgot a 1 in there. Jeez. These two intersect over here, which is at 11 pi over 6, but we can't use 11 pi over 6. We actually wanted to go backwards, but because I'm graphing from 0 to 2 pi, it wouldn't let me trace backwards. So I'm actually starting this region at negative pi over 6 as my lower limit of integration, the equivalent angle to 11 pi over 6. And there's my integral setup to find the area between those two curves. So I'm going to have 1/2 times, I'm pretty sure I forgot the 1/2 in the first example. My apologies. Negative pi over 6 to 7 pi over 6. And I get 24.187. And that's the area inside of the curve, r equals 3 plus 2 sine of theta, and outside of the curve, r equals 2. Just going back for a second, our answer here should be, in example 1, should be half of what it is, so it should be 2.174, since I forgot that half when I first calculated it. Alright, that's the end of this video. We're going to stop today. We'll come back in the next video. We'll look at examples 3 and 4, and finish off this lesson on areas involving polar curves. Alright, see you guys then. Have a great rest of your day.